Right. Ready? So good morning all of you. The summary of the last lecture, we have discussed this lattice vibration contribution to the specific heat. And one more thing is there, free electron contribution. Now take a fresh page and put the heading, free electron contribution. This is a very important. Most of the questions from SSP you have from this part only. This is a very crucial. Pay attention. Free electron contribution. Contribution of specific heats. Of specific heat. Heat of solids. Okay. So here we are going to consider this free electron contribution. If you want to study this, first we have to study one more thing, that is free electron gas. That means how the free electrons are distributed you have to know. That's why we are going to study the free electron distribution first by using quantum mechanics, nothing else. Okay. So here I am taking this free electron gas, free electron gas. Sir, what is the meaning of a free electron gas here? That too ideal case we are taking, that means ideal gas. What is the ideal gas? Potential energy equal to 0. Now you have a doubt. Sir, which case you are considering? Relativistic or non-relativistic? Non-relativistic. So I am considering this free electron gas, which one? Non-relativistic. Babu, very important, very crucial. Listen carefully. So, okay, the non-relativistic means everybody know the energy, no potential energy, only kinetic energy. How much? If you say fast, it will go fast. Come on, h cross square k square by 2m. Already we have derived all these things, but wait. But now we are doing very fast. Okay, 2m E by h cross square under root. That implies you have to know one more thing, dk. That is under root 2m by h cross square 1 by 2 root e dE. Super. So all these things you must remember. One more time. Here what we are discussing in the first task. First we have to know how these electrons are distributed. How many electrons are there? What is the density of states and which electrons are contributing. For example, I say 100 electrons are contributing. How much? 100. Each electron energy is what? 3 by 2 kBT, because it can move along the 3 directions, x, y, z, degree of freedom 3. Once I know how many electrons are participating in the process, then I will multiply that number of electrons which are participating into each electron energy. How much? 3 by 2 kBT. Then what I will get? The increase in the energy of the lattice. That is nothing but what? U. From the beginning onwards we are finding U. U lattice vibrations, here U free electron. The amount of energy increased due to free electrons. Once you got that, CV equal to dou U by dou T. So that's why our first aim is to find, here 100 students are there. For example, all 100 students won't participate in the discussion. Why? Their knowledge is not sufficient. The same way, all electrons won't participate in the process. Why? Whatever the energy you are giving, they are not ready to take. Why? That energy is not sufficient to go to higher states. So what higher state, what lower state, everything we will discuss in this concept, very crucial, ready. Okay, that's it, and this is the non-relativistic case we are taking. Now first we have to get the density of states. Although you have done, here we are doing one more time, density of states. I am not doing, you are going to do. Wait, 1D. First take 1D. 1D density of states means number of states you have to find. N equal to length. What is the length here? K. What is the length of pi by L? Length by length is number. And unfortunately, this must be multiplied with that's good. L by 2 pi into k. So what you have to do is just find a dn, L by 2 pi into dk. So please substitute that dk here. Just first one I am doing, L by 2 pi 2m by h cross square whole power 1 by 2. I think that is this is how much amma? 4 pi e raised to minus 1 by 2 d. That's it. So what is this dn? This is the number of states within the energy range E to E plus dE. Number of particles in the range E to, don't forget. And this one we defined as, what is that? G of E. G of, is it clear? Actually this is the density of states, which is a G of E dE. But what is a G of D? G of E? Must remember, this is the G of E one dimension, L by 4 pi, 2m by h cross square whole power 1 by 2, e raised to minus 1 by 2. So finally, this implies G of E one dimension is a proportional to e raised to minus 1. Like this, I request you do for a 2D and 3D. Start. Make it fast. Don't turn the pages and do it yourself. Just find G of E. Or if you have any confusion, this dn is nothing but G of E dE. G of E dE. If you want more, what is this dn exactly, if you want to know, I am writing here. Yeah, where is the space? Yeah. Number of particles in the energy range, in the range E to E plus dE. I want to ask you one question. I got a dn, that is the number of particles in the energy range E to E plus dE. I want a total number of particles. What I will do? Don't forget that dn. For 2 dimension, n equal to area pi k square by pi by L whole square. Make it fast, please make it fast. And for valid, you have to multiply with the 1 by 4. So this is L square by pi, 4 pi into k square. L square you can write it as a area. dn equal to area by 4 pi into 2k dk. Please substitute that 2k dk. Do it yourself, be confident, you will get a lot of confidence. Come on, do it yourself. Already we have done in the last classes. Here better to substitute 2k dk. That's why k square equal to 2me by h cross square. From this find differentiation, that is a 2k dk, and substitute. In 3 dimension, that is a volume 4/3 pi k cube by pi by L whole cube. Please simplify. And for valid number, you have to multiply with 1 by 8. I think here you got 2m by h cross square dE. Please take it and substitute. dN equal to area by 4 pi and 2k dk, 2m by h cross square into dE. So I told you already, this is the g of E dE. Don't forget this, g of E dE. So what is g of E? G of E equal to area by 4 pi into 2m by h cross square. So that's, please write g of E is proportional to e power 0. In which dimension? 2 dimension. This is which dimension? 1 dimension. Next 3 dimension, do it. Today we are doing with the 3 dimension. 1 dimension, 2 dimension is your homework. Whatever I derived, I will tell you what you have to do in the homework. So first I will derive everything from the 3 dimension, and after that you have to do 1 and 2D. In CSIR they will ask any 1 dimension, anything. So be careful. And once you have finished, please draw the graphs. Density of states versus energy, 1 dimension, 2 dimension, 3 dimension graphs. I think here you got how much volume by 6 pi square, I think 6 pi square k cube. All of you got this? Now again differentiate it, that is V by 6 pi square into 3k square dk, and you can substitute this k square and dk. This is V by 2 pi square. If you substitute k square, how much it is? 2me by h cross square, and dk under root 2m by h cross square 1 by 2 root e d. So I hope you got, this is a V by 4 pi square 2m by h cross square whole power 3 by 2 and e power minus, sorry, this is e and this is root e, that is why e power 1 by 2 dE. Just now I told you this is the number of particles within the energy range E to E plus dE, that is why we will represent with the G of E dE. So this is our G of E. So G of E in 3 dimension equal to V by 4 pi square 2m by h cross square whole power 3 by 2 e power 1 by 2. I think you have drawn the second one without problem. It is a constant, right? Constant means what? You will take a constant straight line. 3 dimension. See, G of E is a proportional to what? E power 1 by 2. Squaring on both sides. G square is proportional to E. E is on x axis. E is on x axis. G is on y axis. Means what is your graph? Y square equal to x. Y square equal to x. Generally, if I say y equal to x square, how you will draw? Parabola. Symmetric about which axis? Y axis. Y is what I said? Y equal to x square. Parabola. Symmetric about? Now I said y square equal to x. Parabola. Symmetric about x axis. X equal to y square na? Y equal to x square. Parabola. Symmetric about y axis. X equal to y square. Parabola. Symmetric about x axis. Next this one. G is proportional to 1 by e raised to minus 1 by 2. As e is tending to 0, what will happen? Or e is tending to infinity, what will happen? 0. So e is tending to 0, infinity. E is tending to infinity, 0. Or else this is 1 by e power minus 1 by 2, okay. This is bring this side, then g into e power something equal to constant, x into y equal to constant. Right, okay. Once again everybody please remember that G of E in 3 dimension. Please remember, please read. G of E in 3 dimension. V by 4 pi square 2m by h cross square whole power 3 by 2. Wait. 2m by h cross square whole power. Whole power. In 2 dimension whole power. In one dimension, whole power. Whole power. 3 for dimension. 2 for this. 2m by h cross square. Dimension. Power. Next. 2m by h cross square. 1 by 2. 1 for dimension. 2 for. So whenever you forgot, 2m by h cross square whole power, dimension by power. Dimension by power. If you forget, otherwise no. Ready? Yeah. Very important. Here we have two cases. Here what we are going to study is first one, free electron gas. Free electron gas at 0 Kelvin. At 0 Kelvin. Another is at not equal to 0 Kelvin. These are the two things we have to study. Sir, what is the speciality of 0 Kelvin? Remember, if you take a system at a 0 Kelvin, I mean Fermi gas at a 0 Kelvin, it's just like a what is that? A new movie released, KGF released. All theaters are houseful. House? Same thing. All benches are full. All states are full. That is called strongly degenerate. The strongly degenerate means strongly degenerate means what? All the states are completely filled. By what? Electrons. Where? At t equal to 0 Kelvin. This is a possible only when t equal to 0. Okay, wait. So free electron gas at 0 Kelvin. This case is called strongly degenerate. I hope you understand the terminology. Strongly degenerate means all the states are completely filled. Weakly degenerate, empty are there. After 2 weeks, theater after 2 weeks. Nowadays only 2 weeks only, na movies. Okay, that's it. After that, OTT. Something like that. Ready. So strongly degenerate means, are you listening? But face expressions not good. So ready. Strongly degenerate means all the states below. You are saying all the states are completely filled. There are infinite number of states. There must be a reference level below which all are completely filled. That level is called Fermi level. All states below Fermi level are completely filled. So that condition is called strongly degenerate. Cool. Now wait a minute. For this, I need to define one thing called distribution function. Babu, listen. I am not deriving, I am explaining, but the derivation is in the another. Sir will explain. Your stat max sir will explain. Distribution function. Distribution function. Am I everybody understand this meaning? What is meant by distribution function? Ready? See this classroom. I want to say the distribution function of this bench, this row. How many benches are there? 2. Here, 2. Okay. How many people are there? There 2. Here 1. Total how many are there? 3. 3 are occupying how many states? 3 by 2. 1 minute. Distribution function means it will tell you how the particles are distributed in the states. For example, I have 5 states, 4 particles occupied. Then what is the distribution function? 4 by 5. Number of particles per states is nothing but what? Distribution function. Everybody understand? Right. Distribution function is defined as f of e. This is simply number of particles occupied by number of states. I hope now you got it, what is the G of E and why you have written that G of E there. Clear? That's it. So f of E is defined as n of E by G. F of E equal to
n of E by G of E.
Good. Okay, and don't forget this because it's very crucial. N of E is always equal to f of E. And you know we are in the 3 dimension. That's why G of E 3 dimension. Don't see that board. Come on, say.
E by 4 pi square 2m by extra square whole power 3 by 2 e power 1 by 2.
That is the G of E. Wait, which gas you have taken? Electron gas. What you said? What gas you have taken? Electron gas. Yeah, E minus and electron gas. E minus gas, electron gas. What you are writing this? States, number of states. Am I right? Which states? Spatial states or spin states? Huh? Yes. You have not discussed anything about the spin till now. I told you, I mean, you know that, I need not to say, you know that. In hydrogen atom, Coulombic degeneracy is n square. That is what? N square space. If you want to spin also, you will multiply with what? 2. What is that 2? 2s plus 1.
2s plus 1.
That's why. Since I have taken electron gas, it is a fermion. It is having a spin degeneracy. Say yes or no? Are you listening? I have to multiply with what? Spin degeneracy how much? How much? If I multiply, then my G of E, once again, here I am writing, okay. G of E in 3 dimension, yeah, including degeneracy, how much? Whatever you are studying, everything will be repeated after few days. Where? Statman. There also free electron theory is, you must study Fermi distribution. Ready? Okay, cool. Now here we have one more derivation, but we are not doing that. Distribution function for Fermi-Dirac statistics. 3 statistics, MB, Fermi-Dirac and Bose-Einstein. Fermi-Dirac just I am giving, but I will derive later. 1 by e raised to alpha plus beta e plus 1.
1 by e raised to alpha plus beta e plus 1.
Bose-Einstein minus 1. And Maxwell-Boltzmann nothing. Maxwell-Boltzmann 1 by
e raised to alpha plus beta e.
Fermi-Dirac
1 by e raised to alpha plus beta e plus 1.
Bose-Einstein
1 by e raised to alpha plus beta e minus 1.
Very crucial. I will derive. Each and everything will derive. Don't get tension. And what is alpha? Alpha is defined as mu beta. Where mu is called a chemical potential. Wait. What is meant by chemical potential? There is a gas. Okay, forget about gas. This is the classroom. What is the chemical potential of this classroom? Who is the last person enter into the class today? Both came at a time. How it is possible? Your trajectory is linear. Okay, ready, listen. First try to understand. See, I am explaining each and everything whatever I am writing. Okay, only derivation this one will come later. Try to understand and don't keep the faces that unknown things are explaining. So this is already we derived, and today we are introducing the spin degeneracy because it is a Fermi gas, electron gas. That's good. Chemical potential. Alpha equal to what? Mu. What is mu? Chemical potential. For example, this is the system. Now let us say 100 students are already occupied. So what is the system energy? Energy of 100 students. Say yes or no? System is made up of you. UV is made up of you. UV energy is you. That's why 100 students are sitting means the system energy is nothing but 100 students energy. Now the 101th student came into the class. Then the system energy raised or decreased? Raised. The amount of energy increased. The amount of energy increased per particle is called chemical potential. Chemical potential means the amount of energy increased per particle, or the amount of energy increased when you add a new particle, a particle. That's why per particle. Clear? Wait. So the chemical potential, amount of energy raised, or RI, or raised per particle is nothing but the chemical potential. Raised ledu, increased. That's good. Okay, fine. Now everyone. So that's why your distribution function Fermi-Dirac statistics become 1 by e raised to minus alpha equal to minus mu beta. Mu is the chemical potential, but alpha formula is minus mu beta. Now alpha is minus mu beta, that's why e raised to beta e minus mu plus 1. Everybody understand? Now what is the distribution function for Fermi-Dirac statistics? Read. 1 by e raised to beta e minus mu plus 1. Now you are considering the system at which temperature? 0. That is what? What is the meaning of that? What is the Fermi level? Last occupied level. Limiting potential. Wait. Now, you are considering at T equal to 0 Kelvin. 1 minute. Please try to understand carefully. Now here I have taken a 1D box. Okay. So this is the ground state. Maximum how many? 2. And here first excited 2. Like that I am distributing. And here also 2 electrons distributed. This energy is E, 4E, 9E. Total how many electrons over? 6. Now a 7th electron is coming. Try to understand carefully. Definitions you can't remember. You can remember only these situations. A 7th electron is entering. That 7th electron, where it will occupy? Which state? This is the first state, second state, third state. To which state it goes? Fourth state. Because your system is strongly degenerate. Say yes or no? If there is any vacancy here, it will come and occupy that vacancy. That is, the system is called weakly degenerate. But your system is already that means up to 3 levels, 1, 2, 3 are completely filled. Then the new electron will enter into which state? Which state? That fourth state is called Fermi level. Okay? Ready? Ready? Now this 7th electron is going and occupying the 4th level. What is the energy of the 4th level? 16. Now tell me, a 7th person entered. Now what is the amount of energy raised? A 7th person entered. What is the amount of energy raised? The 7th electron is sitting on the 4th level. 4th level energy is what? 16. Now the system gains how much extra energy? 16 EM. It is occupying the 4th level. Earlier any particle? What is the energy of your system till now? E plus 4E plus 9E. Total 14E. That's it. Now the seventh electron is going, new particle is entering and occupying which level? Fermi level. Which level? Fermi level. Now you are adding one particle. That means how much you are adding energy? 16. The amount of energy raised. 16. The amount of energy raised is nothing but. Now the chemical potential is nothing but which energy level? That's why at t equal to 0, that's why at t equal to 0 already written. So this is the Fermi energy. That's why the amount of energy raised is nothing but wherever the last particle is going, that level is what? That's it. But remember, this is only at 0 Kelvin. Only when your system is strongly degenerate. In case any gap is there, it will go and occupy this level. Then how much energy increased? 4e. Array, wherever I am sitting, that is the energy of the system added, extra energy. Understand? Why you are saying 7? Difference. Ready? Understanding? So what is the chemical potential at T equal to 0 Kelvin? Fermi. What is the Fermi energy? Last occupied energy. The last occupied energy is nothing but the Fermi energy. That last occupied level is nothing but a Fermi level. Understand? Good. So that's why the distribution function f of e become, come on say, e raised to beta e minus ef plus 1. Which case ma? Strongly degenerate case. Try to understand what I defined here. This is the distribution function, alpha equal to minus mu beta. Mu is the chemical potential. Amount of energy increased by adding one particle. In this example, you are adding the seventh particle. How much energy you are giving? 16e. That is the last level. That's why Fermi level. That energy is Fermi energy. How much energy increased means Fermi energy. So mu equal to Fermi energy. Clear? Now finally we got ready. So the distribution function f of e at t equal to 0 Kelvin, you got 1 by e raised to beta e minus ef plus 1. Now ready. I am taking the first case. Okay, I am taking at t equal to 0 Kelvin. Okay, that's why I can use this. And I am considering E less than EF. E less than EF. If I take E less than EF, what will happen? See, f of E equal to 1 by e raised to, t equal to 0. Then beta equal to what? Why? Very slowly saying, some people are not at all opening your mouth. Otherwise, get out of this class. What is the use of sitting there? Beta equal to what? That's why beta equal to infinity. So this is infinity. Now E less than, EF. Then E minus EF negative or positive? Negative. Plus 1. So E raised to minus infinity. 0. That's why. How much? 1. The distribution function equal to 1. When? E less than EF. F of E I defined as N of E by G of E equal to 1. Number of particles equal to number of states. Actually here we want to take 2 electrons per each. We will consider that the spin states also separate. Okay. So earlier in quantum mechanics, we will take one state, we will keep 2 particles here. But that 2 states we will represent 2 different states here, because the spin degeneracy also included. That's why this is up state, this is down state. That's why only 1 particle per each state. That is the difference between stat mech and quantum mechanics. Quantum mechanics will take the only space, spin state line we won't draw. There itself we will draw 2 up, down. But here we will take that up and down also two separate state. That's why one per each state. Is that clear? That's it. So here this implies what? Number of states equal to number of particles equal to. Next, second one. Same. At T equal to 0 Kelvin. Now I am taking E greater than EF. Ready? F of E equal to 1 by E raised to beta. Very few people are saying. Are you interested? Otherwise we will leave. We'll take rest. E minus EF. Positive. Plus 1. 1 by infinity. 0. 1 by infinity is 0. Now tell me. N of E by G of E equal to 0. That implies N of E equal to 0. States are there. Infinite number of states will be there. Particles are not there. Now this classroom is over. Anyone will be there? No. Class is over. Anyone will be there? After 24th MO, anyone will be there? No. Empty. No particles. States are there. Benches are there. So finally, this is f of E, distribution function, and energy. Somewhere we have Fermi energy. This is 0. Now at T equal to 0 Kelvin, E less than EF. For all E less than EF, F of E value, F of E value 1. Okay, that means up to E equal to EF, your F of E is 1. And beyond E equal to EF, F of E 0. Clear? That's it. Now this is the graph where at T equal to 0 Kelvin. Right? Actually what will happen? This is the Fermi level. We will find that Fermi level, don't worry. And this side, left side of Fermi level and the right side of Fermi level. Carefully understand. This side you are having electrons now because all the states are filled. Say yes or no? These are what? Electrons, 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 something like this. Now what will happen? This is at T equal to 0 Kelvin. Now I am increasing the temperature. Once I increase the temperature, the electrons which are just below the Fermi level gain thermal energy and they will jump out of that. They will jump and occupy the higher levels. Then here you will get holes, okay, and here you will get electrons. That means once the temperature is increased, your distribution function will be like this. Means all these electrons vacating their sides and occupying the higher level. Here you will get a valency band and here you will get a conduction band. So the Fermi level is lying exactly in the between valence and conduction band for intrinsic semiconductor. Okay, that we will discuss, don't worry. I hope you understand what is happening here. And one more thing, I want to find this. Means what is this point? Carefully observe. This yellow color is what? Yellow color is what? T is not equal to 0. At this point, your energy is what? Yes. Now let us see. Now again, I am checking second condition. T is not equal to 0 Kelvin, but I would like to check E equal to EF at this point. I hope you are observing. Now go to the distribution function. F of E equal to 1 by, I cannot write beta infinity here. It's a simply, but unfortunately, E minus EF 0 plus answer. Oh, exactly how much? So At T is not equal to 0 Kelvin, once your energy become, and at E equal to EF, energy of the system E equal to EF, half of the levels are empty, half of the levels are filled. At Fermi level, if the energy equal to Fermi level, then and the temperature is not equal to 0 Kelvin. This indicates a distribution function how much? What is the meaning of distribution function? Half. Number of particles by number of states is equal to half. Half are filled, half are empty. Is that clear? Come on. At Fermi level, energy of the system is equal to Fermi level. That means it is equal to Fermi level energy. Then half of the states are filled and half are the empty. You increase the temperature, na, then half of the electrons will go and occupy the higher levels beyond the Fermi level. Now let us say your states are like this. All these are filled. Okay, let us say 10 states are there. 10 states you have 10 electrons. Now 10 electrons are there, each state 10 electrons. Now you increase the temperature. Okay, now what is the energy of the system right now? E equal to EF. Okay, because already filled above. So what is the maximum possible energy there? EF. The total energy of the system is Fermi level. Okay, EF. Sum of all, but here the energy of the system is become EF. That means what is E exactly? If you are adding the particles, generally if you are adding the particles, the amount of energy is increasing. Or let us, what exactly equal to EF? Wait, I will come back to that. So at E equal to EF, what is happening? Half of the electrons vacate their sites and they will go and occupy the conduction band. Here we are getting a vacancy and there we are getting an electron, free electron there. That is happening. And half of will vacate and half will occupy. That is the meaning of half empty and half occupied. Now what exactly E? You have to see. What is E there? E is the energy of the level actually. Each level. Each level is the energy. So at Fermi level means again it is not connecting. Total energy of the system is not Fermi level now. Total energy is not the Fermi level. Okay, so we will see, maybe next discussion it will come. It is not connecting here. From the distribution function, we have taken energy less than EF. That means below the Fermi level. What about the energy levels of below the Fermi level? All are occupied because we got 1. And beyond Fermi level, that means E stands for energy of the levels. E stands for energy of each level, which are above the Fermi level, which are below the Fermi level. So E greater than EF, F of E got 0. That means those levels are empty. That's why that line, orange line is at 0 Kelvin. But here just we are checking as a T increasing what is happening. The curiosity at E equal to EF is what happening. So half of the states empty and half of the states filled. Wait, you will understand. Actually, that is the thermal excitation process. Due to that excitation only, lattice energy is increasing. Maybe once the discussion is completed, maybe you will get an idea. Just wait. Here we are unable to connect. Is it correct? That side conduction, this side valence. Where you are getting holes is a valence band, na? Sorry. Correct. Electrons filled is a conduction band. Correct only, na? Correct only. Intrinsic semiconductor, Fermi energy level lies exactly in between conduction and valency band. If it is a p-type material, the Fermi energy level close to what? Valency band. If it is a n-type material, the Fermi energy level close to what? Conduction band. Understand and write, very crucial, very important. Not only for SSP, for SM also. Written only one board, but many things I explained. I didn't write any sentences there. If you read the book, then you will remember. I explained what is a Fermi energy, what is a chemical potential, everything I explained. My bad habit is I won't give the points. You should remember. That was your set question. At E equal to EF, T is not equal to 0 Kelvin, distribution function equal to half. Half of the states filled, half of the states empty. What is the meaning? That just wait. We have to find a number of electrons actually. While you are reading the book, please write the points whatever you find. If you didn't understand the point, please ask. Ready for the most important part of this part? Don't simply copy. If you are copying means you didn't listen properly. Maybe I think at E equal to F, at E equal to F, you are seeing at the Fermi level, below the Fermi level half are empty and above the Fermi level half are filled. Maybe I think that is the point. That is the meaning of half. At the Fermi level you are seeing. So okay, that is not the energy of the system. E is what? Energy of a particular level. That level is what? EF. Now you have already strongly degenerate. What is your Fermi level? One particular Fermi level is the state. Okay. Now we increase the temperature. Okay. So to certain amount. Again you are observing with respect to Fermi level only. Then what he is saying is exactly half will be filled and half will be empty. What is that temperature? We don't know. We have to find at what particular temperature it will be. A distribution curve is like this. This is not the correct graph. This is not the correct graph. Number of particles graph will come, just wait. That is only distribution function. Distribution function won't give the number of states or number of particles. Just wait, that's what I told you, wait. Ready? Now all of you please. Now this is a very important. Ready? Yes, now, so here we have to find total how many number of electrons are there and what is the Fermi level, what is the Fermi energy, what is the average energy, everything we have to find. Okay, wait. So just a few minutes back I defined Dn. Dn I told you these are the number of electrons in the energy range. In the energy range, I hope you remember, energy range, E to E plus D. If you are saying the answer, I will get interest, otherwise no. Okay, now what I am taking is, I am defining this as N of E dE. N of E dE, just I am taking. N of E dE is nothing but what? Good. Now first one, I want to find the total number of electrons in the system. That is nothing but integral Dn, which is nothing but integral N of E. Okay, just a few minutes back we have discussed something. Distribution function f of E equal to, that implies, could you please tell me what is N of E? So this is nothing but integral f of E g of E d. I hope everybody understand. Just from the definition of distribution function, N of E equal to, you are finding total number. That's why from where to where? Unfortunately, your distribution function f of E equal to 1 for energy less than EF, 0 energy, because here the variable is energy and the limits are energy only, but you cannot take 0 to infinity. Why? Up to Fermi level it is 1, beyond Fermi level it is 0. Split the integral, 0 to EF, EF to infinity, EF to infinity, Understand? That's why n total equal to, I cannot take up to infinity, only why? Fermi energy, sorry, f of E equal to g of E. I told you, please remember, please remember. V by 4 pi square is without spin degeneracy, V by 2 pi square is with Tz. Now V outside, everything is constant outside. Now e power 1 by 2, e power 3 by 2 by, and limits 0 to EF, that's why. Any trouble? Shall I write directly? Now this 2 gets cancelled. Total number of electrons, V by after the explanation, my humble request, don't copy, do it yourself. Wait. So these are the number of electrons, total number of electrons participating, because it's a strongly degenerate system. All of your electrons are filled up to Fermi level, okay? So that's, am I right? So that's why, how many electrons are total, not participating, total number of electrons in the system, this much, clear? 1 second. From this, I would like to find, more important, EF power 3 by 2. Shall I bring this everything that side? Yeah, first bring this term that side. H cross square by 2m whole power. Now I am bringing this 3 pi square. Okay na? Now I would like to find the Fermi level, EF, Fermi level. All of you observing? The Fermi level EF equal to whole power 3 by 2. Make it whole power 2 by 3. H cross square by 2m, 3 by 2, 2 by 3. Come on. Whole power n by v. Number, density, concentration. Concentration of electrons. Number of electrons per unit volume, concentration of electrons. So finally, this is my Fermi energy at 0 Kelvin. That's why they will write this as EF of 0. EF of 0. What is the meaning of 0? 0 Kelvin. Unfortunately, if your system is strongly degenerate at a T equal to 0 Kelvin, Fermi energy independent of temperature. If it is not strongly degenerate, Fermi energy varies with respect to temperature. That also we have to derive. First today let us focus on this. Are you understanding? Since your system is strongly degenerate, all the states are empty, Fermi level energy does not depend upon the system. Although you are increasing the temperature, the system Fermi level is a constant. Understand? Any temperature term. That's why the Fermi energy is proportional to what? N power. It's a proportional to, Amma, this is the CSIR question. What is the question? They have given the number of particles per density increased by 4 times. Then Fermi level is increased by what? That's the question. 5 times, 4 times, or 8 times, or something they have given. I think 8 times. 8 power 2 by 3. 8 is what? 2q. 3 gets cancelled. Answer 4. So Fermi energy is proportional to? Wait. So that's why what is happening here? If I take an intrinsic semiconductor, this is the conduction band, and this is the valency band, then it is exactly fine valence kinda sure wrong avval chepta, right? So this is the Fermi level. The notation, generally people whatever they are following we have to follow, we should not change the things. Generally conduction band above a so Fermi level is exactly in the middle because it depends only on the concentration. This is the intrinsic, that's why number of electrons concentration, number of holes concentration, both are same. This is the intrinsic. Which one? Intrinsic. For example, you have some other, wait a minute, and you said this is the conduction, and you said this is the valence, and here your Fermi level is very close to the conduction band. This is your Fermi level. So Fermi level is close to conduction band means here number of electron concentration is greater than number of holes concentration. That's why this is a which type? N type. And similarly, if you take this is the valence band and the conduction band, and the Fermi level is close to this valence band. Here what is happening? Number of holes is greater than number of electrons. That's why this is which type? P type. But whenever you combine this P type and N type material, what will happen? So if I combine this P type and N type material, you know PN junction diode will be there. This is the P type material, N type material, and this P type is having some Fermi level, then we call it as a EF1, let us say, okay, and the N side also you have one Fermi level, okay, so one Fermi level, this is the, let us say, EF P or EF N. This is the Fermi level on P side and this is the Fermi level on N side. The difference between these two Fermi levels is nothing but barrier potential. Barrier potential or barrier potential width or something like that. 0.7, 0.3 silicon and germanium something. So what is that barrier potential exactly? It is the difference between the Fermi level energies between P type as well as N type. Come on. Reverse, huh? In my notebook I have written below conduction, above valence. I don't know what is correct. Anything is okay. Conduction band is above. Correct. Actually, the electrons will go from this state to that state. Good. My proof చూపిస్తాను. She is showing the proof. Holes. Valence band holes. You are here the electrons are vacating and going here. Vacating is nothing but the holes and occupying is nothing but the electrons. What? Intrinsic semiconductor, concentration of holes and concentration of electrons both are same. That was the gate question. One graph is given. Which of the following represent the graph for P type material? One gate question was there. That means it is close to the P type means valence band, N type means close to the conduction band. not only simply doing, you must remember plenty of CSR questions are there based on this. Fermi energy h cross square by 2m 3 pi square n whole power 2 by 3. Please write 2-3 times, or at least after the class take the rough papers and once again practice all the things and then throw it, not notebook, papers. Read the book, after that read the book, then clear. We didn't explain any semiconductor devices now. Only PN junction diode we explained. Semiconductor part I didn't explain. So first we got the total number of particles, we got V by 3 pi square 2m by h cross square whole power 3 by 2 into EF power 3 by 2. That is the total number we got. And after that Fermi energy we got. What is the Fermi energy? EF equal to, come on I say, h cross square by 2m 3 pi square n whole power 2 by 3. 2 by 3, don't forget. That was the previous CSIR question. Shall I ask one more question? Fermi temperature is proportional to what? Fermi temperature is, Fermi energy is proportional to n power 2 by 3. Fermi temperature. Huh? Energy is nothing but KT, KBT. Energy is nothing but KBT. Oh, Subhamma. Energy is nothing but KBT. EF is nothing but KBTF. Okay, that's why TF is proportional to. If anybody asks what is the Fermi temperature, EF equal to KBTF. So TF equal to h cross square by 2m KB. If anybody asks what is the Fermi velocity, ready? Non-relativistic or relativistic? Non-relativistic kinetic energy, half mv square. Half mv square equal to this. Vf square, you will get it. Next, somebody ask Fermi momentum. Energy equal to Pf square by 2m. Understand? Like that, whatever you want, you can find. Fermi temperature, Fermi velocity, Fermi momentum, Fermi. Ready? Oh, board is here, I explained there. Okay. Ready? So simply EF can be written as KBTF. EF can be written as half mVF square. EF can be written as PF square by 2m. Whatever you want, you just write. Amma, stop. Okay, from this I got one beautiful expression, Fermi energy at 0 Kelvin. Come on, I say H cross square by 2m, 3 pi square n whole power. Wait. Now, I would like to find E total. E total. Ready? Stop. Earlier you have taken number of electrons in the energy range. Number of electrons in the energy range. N of E. That dn. dn anna n of E, dE both are same. What is this ma? Number of electrons. Wait. Number of electrons in the energy range. E to E plus D. 1 minute. Each electron is having energy E. Okay. Now I want to find the total energy. Everyone please see. Now I am taking N of E dE. This is the number of electrons in the energy range. Each electron energy is E. Now I want total integrate. E is a variable because you have taken only E to E plus dE. That is how much? N of E dE. In that range, what is the energy of each electron? E. So this is nothing but energy of the electrons in the energy range E to E plus dE. I want total from where to where? Understand? Now you already defined. Could you please tell me what is N of E? N of E equal to? Because F of E equal to N of E by. Now this is 0 to infinity. So this is F of E. Okay. And E, G of E, D. Now G of E is nothing but now F of E equal to 1 if energy less than. That's why 0 to EF. Let me write constants outside. You can do it now. Start. Because this is a 1, 0 to EF. Here it is E, here it is E, E power 3 by 2 dE. This is the total energy of the system. What you are finding is the total energy of the system. Once you got that, third one, average energy. Average energy E bar equal to total energy by total number. Just divide both. Careful amma, don't neglect. It's a 5 marks. Each question is a 5 marks. Don't copy, don't copy, do it yourself. Once you got the total energy, please find the average energy and tell me how much you are getting average energy. I think total energy you got V by 3 pi square or 5 pi square. V by 5 pi square 2m by h cross square whole power 3 by 2 EF power 5 by 2. The total energy V by 5 pi square 2m by h cross square whole power 3 by 2 EF power 5 by 2. I think once you divided both, so average energy, I am taking U or E bar, anything you can take, no issue. Average energy E bar or U, anything you please take. Internal energy, average energy, E bar, U, anything. So E by N, how much amma? I think 3 by 5, 3 by 5. So this one and this one gets cancelled. V by pi square cancel. I think you got EF. Please check. All of you got this? Ready? So U equal to 3 by 5 EF. 1 minute. Amma, what you have taken? Ideal gas. Say yes or no? Ideal gas. Do you know what is ideal gas equation? Ideal gas equation. PV equal to? PV equal to nRT. Any other formula is there? PV equal to average energy and PV, any relation, do you know? PV equal to two-third of EF, two-third of average energy, 2 by 3 U, intermediate. PV equal to two-third U. Don't know. Okay. So, okay, U equal to 3 by 5 EF. So, what is the exact equation? Let me check. Two-third U. Right, listen. So, here we have taken ideal gas. One more equation from our intermediate, maybe you forgot, no problem. PV equal to two-third U. Two-third of U for average energy. Now I am taking this Fermi system, that's why PV equal to, ready 2 by 3, what is the average energy you got? 3 by 5 EF, 3 gets, now PV equal to 2 by 5 EF. So PV equal to, this is also one of the equation, please remember, don't forget, PV equal to 2 by 5 times Fermi energy, just write. That's it. Now what are the required things? Everything is over. Now contribution of free electrons to the specific heat. Come to the final discussion. The climax came. Once I request you, please remember N of E, that means this one, N of E, capital N, V by 3 pi square, 2m by h cross square, whole power 3 by 2, e power 1 by 2. 1 by 2 or 3 by 2? 3 by 2. Density of states also remember, V by 2 pi square, 2m by h cross square, whole power 3 by 2, e power 1 by 2. And what is the average energy? Average energy of the Fermi gas at a T equal to 0 Kelvin, 3 by 5 EF. If you are writing a set exam, if you go and open your papers every year, generally common question, the average energy in terms of Fermi energy and PV in terms of Fermi energy, all these things are very important, don't neglect. Stop. So contribution of free electrons to the specific heat. Now let us discuss. Are you ready? Stop. Now here, if you observe carefully, first we derived the, derived the number of electrons total. That is V by 2 pi square, 2m by h, 3 pi square, sorry. V by 3 pi square, 2m by h cross square, whole power 3 by 2, e power 3 by 2. Say yes or no? Huh? Now we are talking about the number of electrons up to Fermi level. That's why N of EF. That's why this is what? EF. While you are explaining only, you have to write. Remember this. Not understood. If you become a teacher, don't write and explain. While you are explaining, write. Then it will understand. Okay. So this is the number of electrons up to Fermi level. That's why this is EF power 3 by 2. Now finally I got this expression. N of EF equal to this much. Is okay? Next, density of states. Density of states already we know, I think, V by 2 pi square, 2m by h cross square, whole power 3 by 2, e power. I want to find the density of states available. Available means up to Fermi level. It's a strongly degenerate. Say yes or no? That's why this is. So these are total number of electrons. Slowly. Available and this is the density of states, available. Right now my system is having this much number of electrons and this much density of states. If I am trying to draw the graph for these two, this is E and this is N of EF, okay, and this is EF, or you can take EF also, no issue. EF power how much? 3 by 2. This is EF power, the remaining is everything is constant. Are you observing? Now this is EF power 3 by 2 and this is EF power 1 by 2. Whose slope is more? Y is equal to x cube and y is equal to x square. Whose slope is more? X. Now n equal to EF power 3 by 2, g equal to EF power 1 by 2. Whose slope is more? Huh? So n is proportional to EF power 3 by 2, If you find the slope dn by de, how much? 3 by 2 into something. dg by de, 1 by 2 into something. That's why whose slope is more? That's why this curve will be more vertical and this curve will be more horizontal. Less slope, more horizontal, more slope, less vertical. And this everything is up to what? EF. This everything is up to what? EF. That's it. So this is the graph at t equal to what? 0 Kelvin. Okay, right. It's a proportional to e power 3 by 2 and at Fermi level EF power 3 by 2. Now again, as usual, at a temperature not equal to 0 Kelvin, what will happen? Something like this. Means the sum of the electrons below the Fermi level vacate their sites and they will occupy the states above Fermi level. And the same thing here also happening like this. Here we are getting empty, something like this. This is t equal to 0 Kelvin and this is t is not equal to 0 Kelvin. Okay, cool. I would like to find something factor n of EF by I would like to find g of EF by n of EF. How much? Please check. This gets cancelled. V by pi square cancel. Here it is 1 by 3. That's why 1 by 3 by 2 3 by 2 EF. Check. Is it? Good. So G of E by N of E equal to how much? 3 by 2 EF. What does it mean? G of E is, number of states greater than number of particles. This is for Fermi-Dirac system. Fermi-Dirac system always number of states must be greater than or equal to number of states. Number of particles. Number of states never be less than number of particles. So, for example, 10 electrons I have given. How many states required minimum? 10. 20 is okay, but less than 10 not possible. If anybody asks, distribute 10 electrons in 9 states, not possible. That is the condition, just remember. Is it okay? First draw the graphs. Now let us discuss how they are contributing to the specific heat and why it is proportional to T. If anybody ask you to draw the x square, y equal to x square graph, what you will do? You will draw parabola, okay? If they ask draw y equal to x cube, what you will do? Same, but slope more. Ante. But antisymmetric. Antisymmetric means negative side negative, that positive side positive. Odd function. Graphs, you should have that some minimum knowledge. Ready? Over. I told you earlier one point. Although there are 100 students won't answer the questions. Only those who are participating in the discussion, who are participating, who are having sufficient knowledge or who are having sufficient interest. Okay. In the same way, although these many number of electrons available up to Fermi level, all are not participating. Why? Listen. Now here I am increasing the temperature. Babu, listen. Once I increase the temperature, how we will increase? In the order of kBT. kBT. So once you have increased the temperature, that means the energy is the increasing in order of kBT. So what will happen? Babu, listen. Now this is the Fermi level. Only those electrons which are below the Fermi level of order of kBT. That means this energy order is EF minus kBT. So the electron which is having the energy of EF order of EF minus kBT. Now what will happen? This electron will gain that thermal energy and that electron will excite to the state and this electron energy become now EF plus kBT. Means if you consider that Fermi level, some electrons are here. The electrons which are very what do you say, there is one word for this, innermost, no, innermost, there is something else. Wait, one word is there, I forgot. Electrons which are deeply situated, means very far away from the Fermi level. The electrons which are far away from the Fermi level. For this electron wants to go to higher level, it need more energy. So that's why what is happening here, the electrons which are very close to the Fermi level of order kBT, within the order of kBT will gain the thermal energy and will excite to the excited state, some other state. Okay. So that means energy become EF minus kBT to EF plus kBT. Why these electron is not participating? Why not participating? 1 second. The energy is not sufficient. the thermal energy is not sufficient. That's why all electrons are not participating. That is very clear. Not all electrons are participating. Wait a minute. I repeat, which electrons are participating? Only those electrons which are in the order of kBT energy. Okay, below the Fermi level, within the order of kBT. One second. I want to find that electrons. Number of electrons. Now these are participants. Participants are participating. Ready? Number is always given by density of states. What is meant by density of states? Number of particles per unit energy. You want to find the number of particles only within the energy of kBT. That's why number of electrons participating equal to density of states into. Is it clear? So finally, this is the density of states. Could you please tell me what is the density of states? G of E. G of E into how much? Now could you please tell me from this expression what is your G of E? G of E equal to, come on, I say 3 by 2 N of EF, okay, into this is a number of electrons which are participating. Participating where? Participating in a running race. Participating in thermal excitation. Thermal excitation. So, G of E equal to 3 by 2. Right. N of E equal to 3 by 2 EF N of E into 1 second. So the number of electrons which are participating in the thermal excitation, once again 3 by 2 EF N of EF into kBT. I repeat, although those so many electrons are there up to Fermi level, but we are taking only those electrons which are within the kBT. That is a G of E into kBT. Good. Okay, so this is the number of electrons which are participating in thermal excitation. Now, each electron, you have given a temperature T, you have increased the temperature T, then how much energy you will get? Half kBT for each degree of freedom. What is the degree of freedom? 3. That's why what is the energy of each electron? 3 by 2K. Now, the amount of energy due to free electrons. Understand? I am finding the amount of energy. How many electrons are participating? N of Ne. Into what is the energy of each electron? I hope you are observing. Now Ne is how much? You are not saying properly. 3 by 2 kBT. So that's it. 9 by 4. Okay. So this is N of EF by EF kB whole square. kB whole square into. Now EF can be written as kBTF. EF is nothing but kBTF. Then kB and square gets cancelled. 9 by 4 N of EF kB into T square by TF. the total increase in the lattice due to free electron excitation. So once you got this, I hope everybody ready. CV equal to dou u by dou t. If you differentiate this t, what you will get? So come on, 9 by 2 NEF KB T by TF. T by TF. You have to write like that. So CV is proportional to T. Don't copy, try to do it yourself. That's why finally we will write a CV equal to alpha T cube plus gamma T. That is the contribution of both. This is the lattice vibration contribution, and this is a free electron contribution. These are the electrons which are participating in the process. How we got means density of states available, but we want only those electrons which are within this energy kBT. Just we multiplied the kBT and we got that number, and after that each electron is having this energy 3 degree of freedom. Every degree of freedom it contributes a half kBT. That's why 3 by 2 kBT. Just multiply and you will get it. So the deeply the electrons which are deeply inside, the energy whatever you are giving is not sufficient for the excitation. That's why they are not participating. Only those electrons below the Fermi level within kBT energy, only those electrons below the Fermi level within the energy kBT are participating in the thermal excitation. That's why contribution is where ma? Numerator, huh? Is it okay? Please write there, only those electrons below the Fermi level within kBT energy are participating. Before writing this, if you want to write before this, only those electrons below the Fermi level within kBT energy are participating in thermal excitation. If anybody asks, lattice contribution is more, free electron contribution is less, in interviews they will ask. Specific heat is alpha T cube plus gamma T. So that indicates what? Free electron contribution is less. Why free electron contribution is less? Conductors are having many free electrons. Then you have to say, boss, not all electrons are not participating, only few electrons below the Fermi level within energy kBT are participating. Remaining electrons are as it is. That's why only less amount of energy is increased. That's why contribution is less. But I request you, please read the book immediately, and you will understand if anything is missing or if I didn't convey properly, so it will be fulfilled. Please write that statement. Only those electrons which are below the Fermi level within kBT energy are participating in thermal excitation. That's it, and tomorrow we'll solve the problems. But meanwhile, what you have to do is, today your homework is, we find the total number, Fermi energy and average energy. I repeat, total number we find. Next, Fermi energy you find. From the total number you find the Fermi energy. From the total number you find again total energy also you find, total energy. Okay, after that average energy. Total 4 things, N, EF, E, E bar. N, EF, E, E bar. What is already it is in the order. These 4 things I want for 1D and 2D. Only the change is what? Density of states. You know what is a G. For example, now you want to find for 1D, capital N equal to integral N of E dE. Acting oddu. Acting is moham balagoddu. Integral N of E dE. Now N of E is what? F of E, G of E. Only change is what? G of E. F of E is 1 below the Fermi level. Like that, for 1 dimension, 2 dimension, you please do it neatly and tell me tomorrow. Tomorrow I will verify the notebooks. Okay, that's it. Only 1D, 2D, only capital N, EF, next capital E and average energy. Okay. Already G of E I have given, please check. Endamma?